Universal gravitational potential energy. This lesson is going to allow us to describe the motions of a system consisting of two objects or systems interacting only via gravitational forces. Universal gravitational potential energy is the potential energy a body has due to its position in a gravitational field, just like the gravitational potential energy we've dealt with before. But now we're going to consider the universal law of gravitation, meaning we're no longer near the surface of a planet. The symbol we use is U sub capital G, and the unit, of course, is joules. Orbital velocity is the linear quantity that shows how fast an orbiting body must travel to maintain a stable orbit, and escape speed or velocity is the minimum speed needed to break free from a celestial body. Whenever there's a body in orbit, remember Kepler's 3 laws of planetary motion. First, all orbits are ellipses with the sun as one focus. Second law, equal sweeps happen in equal time, which means a body moves faster when near the star. And finally, Kepler's 3rd law of planetary motion, which we have done an in-depth derivation of previously, t squared is proportional to r cubed. Unless we haven't done the derivation, then we'll do it later. Gravitational potential energy is the potential energy a body has due to its position in a gravitational field. Universal gravitational potential energy is the potential energy a body has due to its position within a gravitational field, but not near the surface of a planet. The equation that we used for the universal law of gravitation is Fg equals big G times big M times little m divided by r squared. For the gravitational potential energy, it's negative G times M divided by R. We've got two equations that look pretty similar to each other. Make sure you're careful in when to use them. When dealing with forces, we use GMM over R squared. When dealing with energies, we use negative GMM over R. If you're asking about that negative, and hopefully you are, think about having two spheres, and they are some distance, their centers are some distance apart from each other. We'll call that R. The gravitational potential energy, when it's here, is going to be at its maximum. If we take that smaller blue planet and we move it away to where gravity no longer acts, remember gravity acts at an infinite range, so we'd have to bring that blue planet to some point infinity. And we could say there's no gravitational force acting at that point, which means it's impossible for work to be done and for that to have any gravitational potential energy. So we would say at that point infinity, there's 0 gravitational potential energy. And at all points in between there, as the blue planet gets closer and closer back to the sun, we are increasing in magnitude, but we are getting more and more negative gravitational potential energy. If that's not enough for you, I've got a more in-depth explanation, but be careful, watch out. Here comes some calculus. If you calculus, it's fine, it's not that big of a deal. If you don't calculus, skip this part, don't listen. We know that for a force that varies, just like the gravitational force, our work equals the integral of f dr. When we plug in our limits, where we had r when the planets were close together, and we have infinity as our ending point, we get this improper integral. Negative GMM over r squared. We're integrating that universal law of gravitation. We have that negative there because as we move the two planets further apart, that gravitational force is acting in the opposite direction of the displacement. So if we bring the planet to the right, the force is acting to the left. So we get this negative sign here. When we pull out all of our constants and do the integral and plug in, we get 0 minus GMM over R. Using our work energy theorem, that tells us that is our change in gravitational potential energy. For kinetic energy, we can think about kinetic energy when we're in a circle. There's this tangential speed that tangential speed when an object is moving in a circle, is called the orbital velocity, the speed needed to maintain a stable orbit. To get the equation for orbital velocity, we can relate the universal law of gravity to the centripetal force, because that's what we do. Net force equals gmm over r squared equals m times v squared over r. Solving for v, skipping all of the algebra, we get the square root of capital G times m divided by r. That's our orbital speed, our tangential velocity. Interchangeable words there. Remember that kinetic energy is 1/2 mv squared. We can plug in that orbital velocity for the v in our kinetic energy to solve for whatever kinetic energy is. And when we do that, we square the square root, so we get 1/2 m times g times m over r. Feeling kind of familiar here. Kinetic energy is negative 1/2 our gravitational potential energy, because our gravitational potential energy is negative. We could also say the magnitude of our kinetic energy equals the magnitude of our gravitational potential energy. This only works when we're dealing with circular orbits. What about that total mechanical energy? So the energy that's changing, going back and forth, kinetic energy and gravitational potential energy, don't change when we're in a circular orbit. Everything is constant at all points. You do see some fluctuations in the distribution of the types when we're in an elliptical orbit, which I'll show you in just a second. So we said the magnitude of kinetic energy equals 1/2 the magnitude of our gravitational potential energy. When we plug that in, realizing that our gravitational potential energy has to be negative, we see that our total mechanical energy equals negative 1/2 our gravitational potential energy. Here's our circular orbit. And as you can see, we have 3 different lines. We have the green line, which is positive. That means it's got to be the kinetic energy. The most negative line, that would be our gravitational potential energy. Meanwhile, the total mechanical energy is 1/2 of the magnitude of our gravitational potential energy. For an elliptical orbit, things start to look a little bit different. Notice that we're getting further and further away from the sun here. Our kinetic energy is going down. We're moving slower, which is what is expected. And our gravitational potential energy is increasing closer to 0. Be careful with that negative. When we add those two magnitudes up, we get our total mechanical energy, which remains constant throughout all of this. The only time it wouldn't remain constant is if an external force acted and did work to knock this out of balance, like an asteroid impacting the planet or something like that. Here, we've reached the maximum, and now we're getting closer, and our kinetic energy is getting closer towards its maximum, and our gravitational potential energy is getting more and more negative. Escape velocity is the velocity needed, the minimum speed needed to break free of a gravitational field. We're going to relate gravitational potential energy and kinetic energy. Remember, kinetic energy equals 1/2 mv squared, and ug is negative gmm over r. Not including the negative here because I'm only considering the magnitude. If I included the negative, we might get something weird when we solve for the escape velocity, because we can't have a negative under the radical. Important equation to know, memorize. Remember that 2 is the only thing that's different between an orbital velocity and the escape velocity. Here's an example. The escape speed for a rocket is VE. What would the rocket's escape speed from the surface of a planet with twice the Earth's mass be? And the same radius as Earth. Pause the video, try it for yourself. Here we go with the solution. Remember, the escape velocity is 2 times g times m over r, under the square root. Because we're doubling the mass, it's like putting a 2 in there, right in front of that mass, which is under the radical. So it's the same thing as multiplying the right side by square root 2. So whatever we do to the right side, we have to do to the left side, multiply by square root 2, and we see our answer is B. Next steps, practice, AI prompt, ask each other, ask me, keep asking until you get it.